I forgot to mention that my name is Chris Tyrrell, and I'm at the Milwaukee Public Museum. And I'm going to give you some insights less into the specific biology and more into resources that we can use for bamboo diagnoses and also kind of looking at these organisms across the landscape. So let's see. Okay, that's a laser pointer, and that is forward. Okay. So if you take away one thing from this symposium, it's going to be this figure, right? Because you've seen it in all three talks. And basically what I was trying to get at here is that bamboos occur all around the world. They're organized into four main clades. And as you heard in our first talk, there's still some conflict as to what is the organization among those four clades, whether we're looking at nuclear data or plastid data or whatever data. So this is a big area that's a TBD to actually sort out what is that evolutionary history among these groups. But I'm going to focus in on just the neotropical woody bamboos. And so this group has 3 subtribes within it. And what's kind of interesting about this is, so this is a graph of time and then the number of species. And if you look at the black line here, that black line represents the number of neotropical woody bamboos that have been described over time. And I think the main takeaway here is there has been a meteoric rise in the number of described species. And these are valid species. These aren't synonyms or combinations. This is actual new basionyms that have been put out there. And the median year for these names is 1993. So that means that half of all of the described neotropical woody bamboos have been described in the last 30-some years, and the other half was described in the previous 200. So it's pretty amazing. We are finding diversity like crazy out there on the landscape. In fact, the most recent one was described about a week ago. So the neotropical woody bamboos consist of 457 species, with more to come, given the non-asymptote of that rise in the number of taxa. And you've seen, throughout these talks, the diversity, morphological diversity among these organisms. So within the neotropical woody bamboos, we have bamboos that have fleshy fruits. We have bamboos that have sticky culms. We have bamboos that have uneven length internodes. And then we have a bamboo that looks like a giant juncus. It's just really weird, very strange. And this diversity kind of leads into a number of challenges when you're trying to identify bamboos. So in particular, the bamboos have a lot of phenotypic plasticity. So the variation in characters on a bamboo can change whether you're looking at the base of the culm or the tip of the culm or the middle of the culm. They can also change whether you're looking at a young plant or an old plant. They can change whether you're looking at a plant that's in the sun or the shade, one that's on a north aspect or a south aspect or a west aspect, or it's on a steep slope or a narrow slope. So lots of variation, maddening amount of phenotypic plasticity. And on top of that plasticity, their general morphology is very complex. In some interpretations, the entire clone of a bamboo is an inflorescence or a synflorescence. And then, as you've heard, so bamboos have this monocarpic life history, right? They live for multiple years, they flower once, and then most of them die. And what that translates to is when we go out into the field to collect, most often we're collecting them in a vegetative condition, in a non-flowering condition. And, unsurprisingly, a lot of the important characteristics for telling them apart occur in the flowering condition. So, all of this leads to some interesting stuff. The group that I work on, the genus I work on, is Rhipidocladum, and this is the original key to the species of Rhipidocladum when it was described in 1973. And you'll go through the couplets, and you get to the bottom couplet, And the user of this key is left to fend for themselves because the last couplet says, if you get down here, it's one of these 6 species, right? So what do we do with this? What do we do when we've got, our expert keys that just sort of throw us to the wolves? And this is kind of fun. I love this. This specimen is one that I came across. So this is Emmett Ujevich, one of my mentors. He's literally a co-author on the book about American bamboos. And he got this specimen and he called it, this is Arthrostylidium species C, so not even a validly published taxon, in the flora of the Venezuelan Guiana. And then if you look, you see, well, Emmett came back, probably a few minutes later, knowing Emmett, and parenthetically he said, or Rhopidocladum species. Right? We can't even put a genus on this. Is it an Arthrostylidium? Is it a Rhopidocladum? So when this is the annotation that the experts put on these specimens, what hope is there for the rest of us, right? Well, there is hope. We live in a world with amazing technological advances. We've got artificial intelligence. We've got specimen databases. And then we've got aggregators of those specimen databases. We have electronic identification keys. We have digital formats to put all of this data together so that different software can interchange information. So we have an incredible diversity of resources. And what I'm really going to talk about today is how I am using these elements, putting them together to try to help us with these challenges in bamboo identification. So let's start off. Now, being a bamboo taxonomist, I will just admit that one of the things that we use as sort of a crutch when we're trying to identify stuff is, where was this thing found? So we're using this geographic aspect to kind of rule out some things that it can't be. And so we've got geocoordinates, right? We database these specimens from different herbaria, or we have observations from iNaturalist. That gives us geographic coordinates. We can plot those on the landscape. But, we are also in the time of an embarrassment of riches about the data of our planet, right? So we have information on digital elevation models for the majority of the world, right? The space shuttle in the early 2000s ran the shuttle radar mission. And so we have digital elevation at a very small scale from everything from 60 degrees north to 60 degrees south. We also have interpolated information about precipitation, temperature, solar radiation, wind speeds. All of this information has been put together. That's the World CLIM data that a lot of you, I'm sure, use. So one of the things that we can do here is we can basically do a geospatial intersection of where these specimens and observations occur with this data, these data layers about what the Earth is like at those points. And if any of you have done species distribution modeling, this is sort of the first step. You generate a niche for your species or a climate envelope or whatever, and then you take that and you project it back onto the map. Well, in a simple way, when we're just looking at taxonomy, we can just do descriptive information about where the organism lives. And in particular with the woody bamboos, elevation seems to be important because a number of them will be restricted to particular elevation bands. So if we can define and graphically show what these elevation bands are, it will help with our identification. Similarly, we know that some species occur in drier habitats and some species occur in wetter habitats. And so we have these profiles to tell us where a species has generally been found. That can help clue in when we're trying to identify new taxa. So let's talk a little bit more about the morphology, right? So typically when we describe bamboos or any plant, right, we'll do a description, we'll state a character, say its leaf width, and then we'll provide that character in the form of a range. So here we have two species, species A, species B, and then species A's range is 9 to 24, let's say, millimeters. And then species B would be 22 to 37 millimeters. And this range information, this is very good range information, right? It can give us a sense of how widely spread the character is, the character states. And it can also tell us about where two taxa may overlap in that particular character. But in order to get these data, they had to come from somewhere, right? So as taxonomists, we take measurements, and those measurements are real data. And I kind of wonder, well, why we're throwing away a lot of things by just giving a range, right? We have actual data that generated these ranges. So why don't we use that data and do something a little more interesting with it? These data, what we can do is we can try to fit these data to a probability distribution function, right? So we can say, what is the density of these data if we make some assumptions about how they're distributed? So in this case, let's say they're just Gaussian distributed, normal distribution of the data. And we fit these curves to them. And now you can see that it's not a very harsh line. It's more of a transition between the two taxa. And when we do this, when we model probability distribution functions, what that can do is if we have an unknown taxon, so say our unknown taxon is 22 millimeter wide leaves, which is in that zone of overlap, well, now we can actually get a relative likelihood for each of the two taxa. So we can say, okay, what is the likelihood of seeing a 22 millimeter wide leaf given species B? And what is the likelihood of seeing a 22 millimeter leaf given species A? And now we have a quantitative comparison between these two taxa. We can see, species B is significantly more likely than species A, given the width of this character. So that's a little bit better than the annotation slip where we just have a question mark on it. We can provide a little more data. Even if we wanted to translate this into a qualitative term like probably or possibly, we're moving forward. But a lot of you are going to say, okay, that's great for one character, but there's hundreds of characters that we can describe about a taxon. So what do we do about that? Well, there's a nice technique. It's called a naive Bayesian classifier. And what this is a iterative process that uses Bayes conditional probability to sort of add together different characters. And what's nice about this, the naive part means that each step of the iteration has no memory or no information about the previous step. And so we can do crazy stuff like mixing normal distributions with categorical data, right? Because there's no assumption between adding the two things together. We just need to have relative likelihoods and a prior probability. So we start off prior probability. You could go with how common a species is, or you could just go with everything is equal and multiply it by your relative likelihood. That yields a posterior probability. The posterior of the first iteration becomes the prior of the next iteration. Then you do the likelihood of this character. You get a new posterior. That feeds into the prior of the next character, and so on and so forth. And eventually, when you're done with all of the characters that you're going to use, what you're left with is a relative probability of your sample, your unknown taxon, given a species, the species that you've defined. And so we can do that for each one of the species that might be in our key and get those relative probabilities among all of the things that we're looking at. So that's the theory behind it. Let's look at it in practice here. So Mexico has 7 species of Rhipidocladum, and 4 of them are very difficult to tell apart when they're vegetative. So these 4, here are the 4 species, Rhipidocladum racemiflorum, Pidieri, Martinezii, and Bartlettii. And I've chosen only 2 characters for simplicity here. I've chosen leaf width and the number of branches. So we've measured the specimens. We've generated our distribution functions for each of them. So the colors correspond. Pink is Martinezii, orange is racemiflorum, Pidieri is blue, and Bartlettii is green. And you can see how their character states are distributed for each of the characters. So if, as a toy example, I took the type specimen from Martinezii and I put in its values, and this is just in an R-Shiny application. So the type specimen had a leaf width of 3 millimeters and 135 branches. And you can see these red lines are the value that I provided as the user of the key. And over here, you can see the number of branches definitely lines up with Martinezii's curve. Here, the leaf width, we're kind of on the tail end, the front tail end, but we're still within that curve for Martinezii. and look at the relative probabilities. So the length of the bar is an indicator of the relative probabilities. Martinezii is by far and away, the best match given these 4 taxa. So that's, just a play example. That's how it should be. But if we take some real specimens that we don't know what they are, that are very challenging, here's an example of an unknown specimen, and this occurred in the overlap zone with Bartlettii and Pityeri. And so given the values, we can see that the leaf width was actually following pretty close to the center of Pityeri's leaf widths, but Pityeri has a very widely spread set of character states for leaf width. Whereas the number of branches is more similar to Racemiflorum or Bartlettii. And so when we run that iterative process, on balance, Bartlettii wins out over Pityeri and Racemiflorum, but Pityeri is a close second. And so this annotation might look something like most likely Pityeri or Bartlettii, but possibly Pityeri, something like that. So another thing we can do with this technique is we can look at something called evidence. So we can have a relative probability, but that relative part is the key thing. It's relative to the taxa that were in the key. So in that key, there were only 4 options. And among those 4 options, we're not sure, how powerful the key was to actually discriminate among the 4 different species we had. So that's what evidence is doing, is it's sort of a measurement of the power of discrimination of this method. And what we're showing is these are different surfaces. So on one axis here, we have the number of branches, and on the other axis is the leaf width, and then on the vertical is that measurement of power. And you'll see these crazy nonlinear surfaces, and that's created by the interaction of all of those distribution functions for each character for each taxon. And so this is what it looks like in 3D. I'm going to jump it down to 2D because it's a little more understandable. So each of the colored areas is positive evidence in favor of a particular species. So we've got the blue, green, orange, pink again. But then you'll notice there's these areas in white down here, and then even this little saddle down in the orange part that don't have any color to it. So this little cloud is in this range of characteristics. So from about 3 millimeters to 7 millimeters leaf width, and somewhere from 0 to 50 branches, this key or these sets of characters are unable to tell us with any power what the particular taxon that we have is. So to get around this, what we need to do is add more characters. So the more characters you add, the stronger you can build up your evidence. Okay, so those are the tools that I've been working on. I'm pulling them all together into a website. It is americanbamboos.org. And what this website is, it's a Symbiota platform. If any of you use Symbiota, it's a museum specimen management database. And on top of those museum specimens, I have all of this functionality that does the geospatial intersections. And it also has this key software built into it. But right now, I'm still building out the morphological data for all of the species so that you can use these keys. What do I want to say about it? There's 80,000 records currently in the system across about 611 different taxa. So those are the neotropical bamboos. And one nice thing is that these profiles, they will change in real time. So, we've got new genera popping up in the Olyraene. As soon as those genera are published, I can update the taxonomy tree, and this system will automatically update and change the profiles for Olyra, which was really widespread, had some wide profiles. It'll contract down to just these specimens that represent the current taxa. So, okay, what do we do? We can achieve probabilistic identifications. We can directly use continuous characters. That's one thing that this feature does that a lot of different identification software can't do right now. It's really discrete characters. And many of these data layers already exist, especially for morphological characteristics. But as we do taxonomy, we're going to require our taxonomists to be a little more quantitative in reporting our information so that we can use these data. All right, with that, I thank you for listening, and I'm happy to take any questions.
Question?
Chris, when you describe a species, you measure some different characters, right?
Yep.
And you put the range.
Yep. Yep. So I do that. Yep.
Okay. So, but using that, how many leaves you can add for the same plant? For
Yeah.
example?
Yeah. So right. So that is an outstanding question that I don't have. I don't have a quantitative answer for you. So on an individual plant, you might have small leaves, you might have big leaves, but then you've got multiple individuals that each have small leaves and each have big leaves. So what I do generally is I measure three. I measure one that looks small, one that looks big, and one that looks in the middle. And then I'll do that for all of the specimens that I have. So that's what I do right now. It's a guideline rule of thumb. There's nothing quantitative to back it up. Yep.
Anna?
I enjoyed that a lot, and it's really cool seeing that. I remember you mentioned this a few years ago, and it's really cool seeing it actually happening, probably going live soon. But I was curious about when you're doing descriptions of of species. A lot of the time there aren't that many specimens available, and sometimes there aren't that many populations either to take from.
Yep.
And I was wondering, in those situations when simply taking 3 leaves from a specimen would not be useful, what should you do?
Yeah. So what I recommend is we just use the data we have. So let's say you have a taxon. It's only known from the type specimen, right? There's only one specimen. What do? We measure what we have, and then we look at that same character across other species, maybe species that have a greater number of specimens. And we look at, well, what is the distribution looking like? Is it a normal distribution? Is it log normal? How are we modeling these species that have a lot more specimens? Then we make the assumption, we say, okay, well, if that's how we're modeling this one, let's just assume that if we had more specimens of this other species, it would follow that same curve. And so we just apply, you get your center based on your one measurement from your one taxa. And then with the spread, there's a couple of options. We could we could average the standard deviations from all of the other taxa, or we could set a arbitrary standard deviation. That's the best we can do because we just don't have the data.
Okay. Yeah. I had a follow-up question as well. What do you think would be the most useful characters for this sort of quantitative work?
The most useful. I envision this as vegetative characters because when it's in flower, I'm happy when something's in flower because then I can really tell what it is. So I started this because I was really frustrated getting these non-flowering specimens, and all I've got is leaf length, leaf width, fimbria, or colors, and whatever. Fimbria, no fimbria, Eduardo's favorite character. So that's how I envisioned it. I'm not sure that that's the most useful. I think the most useful characters are the ones that are easily interpreted by the key user. So something that is easy for a person who's trying to use the key to see or measure or identify.
Okay.
Yeah.
And I guess what would be your favorites there?
Of characters?
Yeah.
Well, if we're in Rhipidocladum, I'd go with the leaf length width ratio because sometimes you get really wide ones and sometimes you get really long, narrow ones. That's probably one of my favorites. Fimbria form and color is another good one. And pubescence, leaf pubescence.
Okay, great, thanks.
Yep.
We have time for another.
Not him.
we we need to fill the time with more questions. Chris, we are discussing Jimena and I about how do you deal. For example, you are using data from descriptions from the
No, from specimen
the
measurements.
specimens.
Yeah.
But what happened with those? How do how can I reconcile the different concept for different characters structure? For example, oral zeta versus fimbriae or the concept.
So how do we say it again? Say the question one more time.
So, for example, you're measure oral zeta,
Yep.
but you have fimbriae. So, and some people say oral zeta to the fimbriae or vice versa.
Oh, I see. Yeah. So that's just choosing. It's choosing a definition and using homologous characteristics, right? So so if it's I see what you're saying. So if you mixed sort of a Guaduini character and an Arthrostylidae character, and it's in the same position and it's a similar looking structure. I don't know. I haven't done that yet. So I guess we'd have to set a definition that was applicable to all of the taxa in the key that you're going to use.
And the other question is about the ontology. You say that.
Yeah.
But
Yeah.
so you are measure some specimens from the herbarium, but some of them could be for the new shoots,
Mhm.
the first leaves for the new, and the other one could be the old one.
Right.
So how can I decide to use only mature plants or only juvenile?
Well, on the one hand, what you could do is you could just measure everything you have, and if you have, there's young plants and old plants, what it's going to do is just kind of spread out each of the characters. But if you have enough characters, ideally, hopefully, that iterative process is going to be able to narrow it down because you'll be pulling from multiple different characters and sort of iterating across all of them. So the hope is, the theory is that you will still arrive at the, a probabilistic identification. It may not, it may be more muddy because you have, you've generated the key using the more variable specimens. But I guess I wouldn't worry about it too much because ideally we want this to be useful for downstream users. And so if they're going to encounter young plants versus old plants, let's put it in the key and let it work itself out. I don't know.
We have time for another. No? Yes.
Very interesting talk. And my question for you is, once you have all the distributions, the normal distributions for several characters, have you used these numbers while writing a descriptive monograph to avoid those qualitative feelings that us taxonomists usually use, like usually, frequently?
Yep.
Have you tried to match your graphs with the frequency?
I have not, but there was a scientist at New York, I think, he studied palms, and he published a couple of papers in the early 2000s, and he actually advocated for, instead of publishing ranges, let's publish a measurement of center and a measurement of spread. And I think in those cases, what was his name? Andrew Henderson? Henderson, yeah. And so he was advocating to use the coefficient of variation, which is sort of the mean divided by square root of standard deviation or something like that. Actually publish that in monographs. So you give your traditional ranges, but then you give this the number of specimens that you measured and then your coefficient of variation. I'm not sure if that exactly answers the question, but one of the nice things, I'm writing a proposal right now for this website. So these morphological measurements that I take from the specimens, they're embedded in the back side of the website in the database. And so those normal distributions can be dynamically generated because as a specimen, when a specimen gets annotated, and if the annotation takes it out of one taxon and puts it in another, those normal curves need to be regenerated because all those measurements now are pulled out of it, right? And so it might change the probability distribution function. So the beautiful thing about this is it's all dynamic and it can happen on the fly. Yep. The flip side is when you change something, if you have an identification that was based on when there was an incorrectly annotated, or not an incorrectly annotated specimen, but an alternatively annotated specimen, now the key is different from when someone had used it before. So there needs to be some kind of process where we version the keys, right? So we said, well, this identification was based on version, 2024 March 14.1, something like that. Yeah.
I have he's me a lot of questions about this apparently.
That's
I was
good.
also curious about, I guess, whether you looked into potentially automating some of the measurements using digitized herbarium specimens, because I mean, this is obviously going to be a tremendous amount of work for anybody working on this to measure all these.
Yep. I haven't specifically, but we were working on, we were doing a tree TCN grant with a large consortium. And in that grant, we were working on a program called Leaf Machine. And Leaf Machine is one of these, measurement, I guess it's artificial intelligence software, looking at identifying leaves from herbarium scans and then getting some outlines and lengths. So that would be the first thing I would look at is Leaf Machine, but I haven't done it yet. It's a work in progress. So.
Right. It'll be cool to see.
Another? So thank you very much.
All right, thank you.